This is the first video for Chapter 2. In this video we'll discuss classes and frequency. This is part of descriptive statistics, and in the text this will be sections 2.1 and 2.2. This topic is certainly not, probably isn't challenging to most people in this class at all, but just for completeness we'll go through these basics. Alright, so basically you've got a bunch of data values. The first thing to do is organize them into classes. If you have qualitative data, then the classes are the categories. They are the classes. You know, if you want to look at political affiliation, you would put each party would be your class, and then you would tally up how many are in each one if that's what you were testing. If you have blood type, you know, you'd have A positive, you know, A negative, B positive, B negative, O positive, negative, and AB plus and minus, and those would be your categories. Now for qualitative data, the classes are intervals, and those intervals, there's some rules for picking the interval. The first rule is that you don't want too many of them or too few of them. 5 to 20 is usually taken as those are good round numbers for the extremes in the number of classes. Now the classes must be mutually exclusive. Think again about the categorical data, about your qualitative data. If your categories are not mutually exclusive, how do you even take data on them? Mutually exclusive means they do not overlap. For example, if your categories were tall and blonde, well, there's some, you know, you can see those categories can overlap, so you couldn't be taking data on them. When you have the qualitative data, they had better be mutually exclusive by design. For your intervals, you want them to be mutually exclusive. You don't want them to overlap. That sort of makes sense. The next thing is they're continuous. Even if you don't have data, say between 1999 and 2005 or something, if you don't have data there, you can't skip that group as a class. The classes have to be continuous. It might have no data in it, still is a class. Okay. Then it has to be exhaustive. That makes sense too. You have to include all the data. All right. And then the classes must have equal width. Sometimes you'll see graphs presented where the bars, say in a histogram, do not have equal width. By and large, they should have equal width though. Here's just an example of how to choose the classes. This is the ages of presidents at inauguration. I think this example came from that another statistics book. The name of that book, which is used in 252, is, whoops, let me get a black pen here. It's Blumen, and it's called Elementary Statistics. Can't even say it. A step-by-step approach, and it is a very good book. So if you need to have another look at something that either my lecture isn't clear on or the Mendenhall text is, you can't get it out of there, go look at Blumen. So this example, this data came from that book. So you want to divide this up into classes. Obviously, you look at it, you can't make much sense out of it in this list. So the first thing to do is find the range of the data from the largest to the smallest. All right, your classes, your classes have to include all those values. You know that already. And the range, say, is 27, and you want to divide it into 7 classes. So you would divide that total, 27, divided by 7, and you would get a width. Well, that's not a very good number. You want nice round numbers. You're trying to sort of showcase the data and show the trends and not have to grapple with things like, you know, something out to 3 decimal places. So you round it up to 4. Okay, so here are your classes. There's 7 of them, I think. Yes. And you rounded it up to 4. But now look, the last point is 54 here, 45, and now it's 46. These classes have to be mutually exclusive, so they don't overlap. If they both were 45, then they'd have a point in common. There's something else called the boundaries between the classes. See, The classes will have the same decimal value as the data, but the boundaries between them will actually coincide and they will have one more decimal place. Of course, since the data has one fewer decimal place, it will never hit right on the boundary. For example, the boundary between these two classes would be 45.5 would be right here. This one would be 49.5. And you see no data value would hit it, but that would be a boundary between this class and this one. The width of the class is this difference. It was 4, remember? 46 minus 2, they gave you 4. It's not the width across the class, it's the width between classes. Okay, and you can, sometimes the midpoints are useful in certain graphs. And we just went through these classes are mutually exclusive because they do not overlap. They're exhaustive since all the data will fit in them. They're continuous. There's no gaps in here, like for example 58 and 61 isn't just missing. And they have equal width. The next step is to create the first frequency distribution, and that's just the tally. Frequency is just how many times a number account falls in the class. The relative frequency distribution is usually given as a percent or perhaps as a decimal. So to get the relative frequency, you take the frequency and you divide by the total number of data values. Cumulative, it accumulates. It accumulates as you go along. The last one will be 100%, and that's easier to show in an example. Here's the same example we had before. Here's a tally. So this is the number of presidents with ages at inauguration between 42 and 45. Here's the number between 66 and 69. 16 of them here are between 54 and 57. And you can change that tally into a number, then you call it frequency. Add up all those frequencies and you get a total down here that you're going to use. You use that to create the relative frequency. So to get the relative frequency, you divide the frequency. 2 divided by 42 and gives you percent, 4.8%. 16 divided by 42 is 38.1%. When you add up all these decimal values, ideally you should get 1. Here you should get 100%. Now the cumulative frequency is the cumulative frequency is a number that occur at that level or below. For example, in this example, this was a bunch of exam scores. How many people had grades between 70 and 79 or below? 12. How many people had grades between 90 and 99 and below? 18. That's right, because there's 18 total scores that we're looking at. To get the cumulative relative frequency, you have to turn that into percent. So you divide by 18, and notice here, of course, it's 100% because everybody is either in this group or less than it because of the criteria placed on classes. So once the data is organized into classes, you usually want to put it as a graph. There's many different types of graphs, as you know. I'll just hit a couple here that you will use in homework. For the quantitative variables, histograms are very common. The x-axis is where you put the classes. Let the tick marks be the edges of the classes. This is why you want to use nice round numbers, and then it comes off really easily in kind of graphing software. The height of the bars of frequency or relative frequency. If you look in some other texts, and sometimes the histogram is the area under the bar has to do with the frequency, and it's more moving towards a probability distribution than it is just data. By and large, histogram is just the frequency is the height of the bar. Sometimes it's a relative frequency. And the bars are right next to each other in a histogram. Now, the classes are continuous. There should be no gaps between them. They don't overlap, but it does look like at the edges they make a jump. Frequency polygon, of course, polygon is a straight line with different slopes and different sections. It's a line with different slopes broken up in different straight line sections. The x-axis again is the classes, tick marks at the limits showing the edges, and the y values of the frequency or relative frequency, and they are given at the midpoint. There's also the box and whisker plot that I will discuss later after we have some more statistical parameters. if the data is quantitative or qualitative, you can present it in a bar graph. A bar graph is a histogram, basically, with spaces between the bars, and the bars can be horizontal. Usually they're horizontal. They can be vertical. For qualitative data, there would be a gap because there really is no overlap, and there's no reason that those points would be right next to each other. So you should see a gap there. Pie charts. Pie charts, oh, they're used in business and a few other places, but by and large, those aren't looked on very highly for informational purposes. The problem is that if you have, okay, look at it like this. I've got a straight line that might look a little better here. Okay, say I make a histogram, and this is coming in like this. It's very easy for me to judge the distance here. I can see that with, visually, I can see that distance very, very much. I can tell that's the difference between those two variables, or those two classes. Now, when you have a pie graph, let me see if I can find a circle here. Well, here's an ellipse. I draw it off nicely, then I'll have a circle. Okay, for a pie graph, this is to give you information so that if somebody ever asks you, you can explain why you don't want to present the data in pie graphs. Okay. Well, that's pretty bad. How about that? Okay, let's say we have another division like this. Okay, the difference in the data for the histogram, the bar graph, is this vertical distance here, which is easy to see. It's easy to eyeball that. The difference in the pie graph is a difference in area between here and here. Well, that's, you can see one's bigger than the other, but you really cannot judge it. How about between here and here? Can you quantitatively tell what that area is just by looking at it? No, it's very hard to judge. So it's because the frequency, or the value here, is the area of this piece of pie, and that's hard to judge. So although pie graphs look nice and people use them a lot, mainly, like I say, mainly in business, they really aren't good for presenting information. For quantitative variables, there's also the Pareto, which is just a bar graph that's ordered. You put the most frequent one first, and actually it conveys a lot of information that way. Quantitative data is also presented in histograms. I'm going to give an example here, or a contrast here, to show you the power of the histogram when it comes to actual data. When you take a statistics class, they give you very sparse data sets, so you don't have to do too much work, although hopefully I'll give you some bigger ones, and you really don't get to see the utility of the graphs. This is a typical graph. Here's the scores on the final exam, and here with the number of students, so this would be the frequency of the ones who score between 0 and 20, 20 and 40, 40 and 60, etc. Okay, now let's look at some raw data. Here's raw data from Old Faithful, presented in 2009. It has quite a bit of numbers in there. Look at all this data. And you look at it, you can't make heads or tails out of it. Now look at it when it's organized into a histogram. There it is, and the results are very impressive. Here's an example. Actually, now I look at it, of a Pareto graph. This is qualitative data. These are excuses for being late for work. The most typical one appears to be traffic, and then a few people cite emergency as a reason that they were late for work. Notice this polygon. This is done a little differently than what I said. This polygon, the points are at the end points instead of being in the middle. Usually you put them in the middle, but this is qualitative data, so things are done a little bit differently here. So these graphs are mainly going to be made by software in this class, so you don't have to do that. You might be saying, well, where are the interesting graphs, like normal distribution or the F distribution? Those are probability distributions. They are not part of descriptive statistics. This chapter 2, is descriptive statistics. It's taking that raw data values and putting them in different usable forms. Okay.